As you can see, the AI is writing code. And the code is automatically converted into node graphs, then injected into a Miliastra Wonderland map. This is the generated node graph result. Since the default prefab has no basic mover, I replaced it with a prefab I created. You can also tell the AI which prefab ID to use. Then, run it and see. For example, this is a piece of standard JS code with some complex control flow. I can just run it in the browser and get the following results in order. And it can be seamlessly compiled into a Miliastra Wonderland node graph. After running, the log shows exactly the same results. This is my newly open-sourced Genshin TS project. Genshin TS is written entirely in standard Typescript syntax, one of the languages AI is best at. So you can develop with any existing AI coding tool, even leveraging the NPM ecosystem, and you also get built-in benefits of code like version control, IntelliSense, easy refactoring and more. Logic-heavy gameplay like Werewolf is much easier to build in code. All function calls, events, and parameters come with full bilingual Chinese-English annotations and full type system support. You can hover to see every detail. On some functions you can even see extra usage notes I added. Hey, I made targeted optimizations for common types like entities, plus a variety of helper functions. Support multiple node graphs from a single file by different IDs. Chained registrations to build complex multi-event graphs. Same IDs across files are automatically merged into one graph. Function compilation support, and features that help modularize projects. In short, I finally got the teaser from last video out before that girl uploader did. Next, you'll also see support for the npm create project template. Compilation support for a universal node graph intermediate JSON format. Support for standard TS control flow like for, switch, if, etc. Automatic type inference for declared variables. Unity 3D and JS style API support. Bilingual event registration and node call support. Precompiled constant expression optimization. Automatic local variable reuse optimization. JS style set timeout and set interval support. Automatic closure capture support. Automatic timer pool support. Automatic timer dispatch aggregation optimization. Automatic dead code elimination. Parallel and incremental compilation. Automatic injection backups and injection safety checks. Map discovery support. Full IntelliSense for entity subtypes and dedicated properties. Built-in prefab resource ID support. And many more features. I'll highlight a few key ones. For more details, see the docs site still under construction. Before diving into those details, I need to mention another open source project. It's not the focus of this video. But before I found it, I spent nearly a month reverse engineering GIA and GIL. That project's reverse engineering approach is more complete than mine, so I integrated it as a third-party module and merged in some data from my own reverse engineering. The work on that project is outstanding, and it's MIT licensed too, so I strongly recommend supporting it as well. Next, here's the introduction to Genshin TS. First, this project can be used in several ways. You can run npm create Genshin TS to create a dev template and start right away. You can also install it as a dependency in another project and use its compiler and injector APIs for your own workflow. You can also install the CLI compiler with npm ig Genshin TS. Then compile and inject a single TS file or a JSON intermediate description. You can also inject an exported or generated GIA directly. I defined a JSON form intermediate representation with readability in mind and programmability, so you can build support for other languages or do metaprogramming on top of it without being locked into my TS approach. After creating a project from the template, you'll see something like this. Just run npm I to install dependencies and start developing. You can run npm run dev to enter watch mode, which incrementally compiles changes and injects them into the map in real time. When you need to inject, you need the exact map file name. I added a gsts maps command, so you can run npm run maps to get the map list. It's sorted by time. Just save once in the editor, and you'll see the most recently updated map here. Then put it in the config to inject. If you have multiple accounts or servers, you can also set them in the config to locate the map directory. The config comes with detailed bilingual comments too. During injection, the CLI tool not only runs internal safety checks, but also creates an extra backup to keep your map data safe. When you use signal send, receive features, if a signal is undefined, the injector will warn you automatically. If the node graph type you declare doesn't match the injection target, the injector will auto-fix it and warn you. If you don't want to use injection, you can generate a GIA from code, import it, and manually copy the node graph contents. Since many people are more familiar with Chinese node and event names, you can just pass lang ZH to see the type system's magic. IntelliSense can directly recognize the Chinese definitions. When defining variables, just use a simple JS object literal for the name, type, and value, then via f, using get or set. You'll see automatic type inference, constraining the types you pass in, without manually choosing types like you do in node graphs. Since you're using code, writing calculations and logic, and control flow no longer requires creating nodes one by one. You can just use familiar, conventional syntax, including advanced flow like return, break, continue, switch, etc. The compiler automatically turns it into node graphs via wiring and condition checks. Of course, if you want full transparency, f calls till include one-to-one node graph flow control definitions, and every other corresponding node. And in code, it's common to write readable, maintainable calculations like this. The compiler won't foolishly turn them into a chain of nodes. That would waste node graph resources. The compiler will automatically try to optimize, for example, a complex block involving multiple operations and 3D vectors. That ends by converting to a string for printing. When compiled to a node graph, you'll see it becomes a single print node, filled with the final computed string. But if I introduce an event parameter into the calculation, the magic happens. You can see it becomes a sum of the two, then converted to a string. You can also disable this optimization in the config, and have it treated as pure node graph computation. For variable computations, the compiler also uses local variable node caching to reduce cost. When you need delays, you no longer need to start timers, create timeout events, check names, and then write the logic. Just use familiar JS set timeout or set interval. Nesting and closure capture are supported too. Canceling timers uses the same JS style code. And this isn't just a simple timer node. For example, in some cases an event happens, and you do something after a delay. If you use a simple timer, and the event fires again before the timer expires, because they share the same name, the second trigger won't create a new timer effect. But in Genshin TS, the compiler will, depending on the case, auto-generate a timer name pool, and cycle through it, to closely match real JS set timeout behavior. You can even add a @GSTS timer pool equals 4 annotation to set the pool size. But that's an advanced use case, and usually unnecessary. Most of the time you can just set it globally in the config. The compiler also aggregates simple timer name checks into a switch to improve performance. For helper functions, the project provides lots of JS style and Unity 3D style APIs. For example, vector 3, cross const equals 1, 2, 3 push 2 filter map length dict, set dict, for each and more. For complex cases that are hard to express with node graphs, like const b equals, ESLint will suggest using dict or raw instead. For example, object operations will also trigger ESLint warnings. There are also global objects and helpers, like quickly getting level entities via level or stage, and the compiler caches the level object in the node graph. To improve query performance, you can directly use stage as a global variable, or use player to query the player directly, or player character to get the player's first controlled character. Other entity types work the same way. Use adder to quickly get attributes, use pose for position, self, destroy, and more. You can hover each one to see its docs. Everything feels natural. For types like stage and player where position doesn't make sense, you'll notice there's no pose property. I added detailed type level optimizations for entities and lots of shortcut methods and properties. When passing parameters, entity types are strictly validated to avoid misuse. Of course, you can always wrap with entity to force a generic type. Using event parameters is just natural callback access. Just like writing normal JS, generic parameters that can't be inferred need manual as type or asdict. Array parameters can be indexed naturally. For each, destructuring, assembling, etc. are compiled into corresponding node graph implementations. Outside the node graph function scope, you can write regular TS code. Use npm libraries and run them at compile time. You can use that to precompile random maps. Physics simulation, reading local spreadsheet data, and so on. To streamline your workflow, you can use functions prefixed with GSTS server to define functions inside the node graph scope, making reuse easy. The compiler handles this too. There are some limits like return. ESLint will tell you these details automatically. If you don't want to use the GSTS server prefix, just wrap it in another function declaration. All of this is powered by TS type level tricks and ESLint constraints, so any modern editor works out of the box and existing AI tools just work. These types and ESLint rules are also recognized by AI to improve code. All node function calls carry real node graph flow semantics, so this TS code can be compiled and published as npm packages. To reuse as Miliastra Wonderland specific libraries. Overall, the workflow feels like Unity development. Write code, compile, attach components, node graphs. For debugging, compilation generates intermediate artifacts. First, the GSTS file, the compiler turns your code into F. Style node graph function calls. You can inspect the node implementation directly. Then it generates a JSON intermediate representation that describes variables, nodes, and connections. Next it generates GIA from the JSON. You can trace these artifacts to find the root cause. Some compile errors also point to specific artifacts. In the future I may provide a visual preview for the JSON to reconstruct the node graph directly, so you can skip checking it in the editor sometimes. The first version of the project may have gaps or bugs in some details. Feel free to join the group or leave feedback on GitHub. Client-side node graphs aren't supported yet. You'll have to wait for me to build them, then I'll make another video. Hey, love you all.